Hi everyone, my name is Jessica Ray, and today we'll be talking about our work on developing domain-specific language abstractions for use in compression. Now our goal with this work is to develop a DSL, or a domain-specific language targeted towards compression. And our motivation is not for us ourselves to develop new compression algorithms. I am not the compression expert, but rather provide language support so that the compression experts can focus fully on the algorithm development rather than having to worry about implementation details. The current compression systems that exist, they're often handcrafted and exceedingly complex, requiring the efforts of many different developers to implement them. And there's a couple different reasons that lead to this complexity beyond the algorithm itself. So the first is that the languages of choice for implementation, such as C and C++, the primitives they provide are very poorly matched to the types of data structures you need in compression. For example, there's a lack of a native multidimensional data type. So a benefit that a DSL provides is that you get a more intuitive programming interface that not only gives you a more concise high-level syntax, but also provides the data structures you need. For example, we can natively provide one of these multidimensional data types for you. Another big problem are optimizations. To make a practical compression implementation, you need good runtime performance, and this requires doing optimizations such as wavefront parallelism and vectorization. Currently, these are often done by hand down at the assembly level, which really ups the complexity factor of the code. So a big benefit of the DSL is that you can design an optimizing compiler around it that has native knowledge of the types of optimizations that need to be done for compression, so it can automatically generate this high performance code for you. So the work that I'll be talking about today has to do with our development of the actual abstractions that the DSL is going to be built around, and in particular, I'm focusing on block-based compression. So the three types of abstractions we've been looking at are data representation, data partitioning, and data traversals. And we believe these abstractions really capture the core structure of these block-based compression algorithms. So data representation has to do with providing better data types that match the data structures you need in compression. So for example, this is where you provide the multidimensional data type that captures all of the necessary spatial information and spatial dependencies that occur in the data. We also want to provide more intuitive data access and also support the different types of operations that happen on the data, such as element-wise and reduction-like operations. And for this, we have a handful of different abstractions that we provide, namely the block, view, stream, and bitstream data types. So for a quick code example here, this shows a simple color conversion kernel. In our code, you can see that it's very concise and simple, and it's easy to figure out what the intent of the algorithm is. If you compare this to an existing implementation, here a lot of the code is dedicated towards mimicking multidimensional data accesses, which really makes the intent of the algorithm get muddled into all of the implementation details. So the next abstraction we have is data partitioning. So obviously a really common operation in block-based partitioning is taking a block and decomposing it down into a bunch of subblocks. So we want to be able to provide a nice tree-like data structure that can capture all of these different options and also provide a high-level syntax for actually defining this tree. Additionally, we want to natively support iteration to the tree so you can make it easy to do things like z-scans. And so for this, we have a p-tree and an-tree data type that capture all this necessary information. Again, for another code example, this one is for partitioning in HEVC. You can see with our data types, you get this nice hierarchical syntax for defining the tree. It's easy to modify the tree. You compare this to an existing implementation, which again, the implementation details really obscure the meaning of the algorithm. It's not clear what the partition is doing. Finally, the data traversal abstraction has to do with things such as zigzag scans and diagonal scans. And what we want to be able to do is capture the temporal dependencies in the data that imply these orderings, provide a high-level syntax for representing the temporal dependencies, and again, support iteration through these data structures. So for this, we have the unit traversal. And for another quick example here of zigzag and diagonal scans, you can see our implementation. We have this concise recursive notation for specifying them, whereas existing implementations, they don't really have one way to represent them. Some of them use these big lookup tables that manually enumerate every single coordinate, and other ones require these big conditional blocks that would be inside of loops. And again, you lose the intent of the algorithm. So before I end, just want to say if you've come across any of your own compression-related implementation challenges, we'd really love to hear about them and see how we can fit them into the DSL. So feel free to reach out. My email is right here, and thanks for listening.